And the depth of the lagoons are like, except the final cell, all the cells should be about 5 feet, and the final cell can be 5 to 10 feet with a minimum of freeboard of 3 feet. That is, from the top of the dike to your water level, it should be minimum 3 feet high. And the slope of the dike should be a minimum of 3:1, so in case you need to mow, you should be able to. Other lagoon design parameters, these are all KDHE minimum requirements. You have to meet this, otherwise you're not going to get approval from the regulatory authority. The detention time, we talked about discharging lagoon, and for discharging lagoon is basically where you need discharge to a receiving stream. And for that, for 2 cells, if you have 2 cells, then the minimum detention time, or in a chemical engineering terminology, we say residence time, it's 150 days. And for greater than 2 cells, 120 days is sufficient. This number is obtained by KDHE based on their vast experience in, for wastewater treatment facilities in Kansas. And the other parameter we need to check, the first one we call hydraulic loading, and the second one is the organic loading, that is the amount of organics you're having in your lagoon. And for the primary cells, the first, usually if it's 3 cells, then first 2 cells, you cannot have more than 34 pounds of BOD per acre. Sometimes your hydraulic load will dictate the size of your lagoon cell, sometimes your organic load will dictate. An integral part of any process design and development is environmental and safety considerations. For example, when it comes to environment, there are a lot of, when we go about doing this project, we have to obtain clearance from about like 12 or 13 governmental agencies like Wildlife and Parks, Fisheries, and US Corps of Engineers, Natural Resources, Soil Conservation, all those things. So environmental protection is very important, and also we have to do something called finding of no significant impact, and based on that we may have to do even further intensive like environmental impact assessment. So for example, groundwater protection is a very important aspect of environment, and so the seepage from the bottom of the lagoon cell or from the dikes of the lagoon cell cannot exceed 0.25 inch per day in Kansas. And it's not only the design, it's not sufficient if you just design your lagoon to restrict your seepage to 1/4 inch per day, but after the completion of the project, we need to have a third party who is also a licensed engineer to do the testing and provide a certification to submit to the state. And there are several safety issues which is addressed in the operation and maintenance manual by the consulting engineer, and which the city keeps in their record. For example, confined space entry for manholes and pump stations, and spills. If there is a spill, then overflow from the lagoon, then how do you handle it? And other OSHA requirements. And for any process development, we designed a process for a purpose. Like for example, the lagoon, what is that we expect from a lagoon is a cleaner effluent of a desired quality. And so here, for a sewage, typical sewage, the influent concentration is like BOD is about 150 milligrams per liter, and TSS about 200 milligrams per liter. And the effluent, usually in the permit limits, the NPDES permit, it's like BOD is like 30 milligrams per liter. You cannot exceed 30 milligrams per liter BOD, and the total suspended solids cannot exceed 80 milligrams per liter. This is to protect our water bodies, like streams and water bodies. Otherwise, you'll have a lot of problems like fish kill or oxygen and deprivation. And based on the receiving stream or water body, how sensitive it is, we can have, the state determines this when they issue the permit. We can have other parameters like the E. coli, which is indicator of the pathogenic microorganisms, and other inorganic and even organic parameters. And it's not only sufficient, you know, as an engineer, you design the process and you implement it, you do the startup, it runs great, and it works fine for the first year. And how do you make sure it works? Like usually there is a design period for any project, like it's like 20 or 30 years or even 50 years. So how do you make sure that your process works fine for like the design period. If it fails after 1 year, then it's not a very sound process system. So what an engineer does is not only develops a process, but we need to address the operation and maintenance issues, and which is basically the process reliability. How reliable is your process in the long run, and what are the operation and maintenance issues that the operator or the management, the owner of the system needs to address. So all these, there are several causes which are addressed by the engineer in the O&M manual and provided to the city. And coming to the heart of the process design, which is the process flow sheet. This is what, as a process designer, you'll be doing every time for a project. So the first thing is to develop a block diagram, and then to go to a process flow sheet and the process flow diagram, and then the instrumentation diagram. Step by step, the complexity increases. So what I've shown here is a very simple block diagram, or a process flow sheet, you can say. The raw wastewater from the service area enters to a bar screen first, where the rags and all this bigger solids are removed or screened out, and your wastewater enters into a pump station where it is pumped. The pump station is usually at like 30 or 40 feet below, and so from there it's pumped to the top of the ground where your lagoon is. And from there, the biological degradation takes place and settling takes place, and finally it's discharged to the receiving stream. And sometimes you may have to have additional processes in the system, like for example chlorination. When you want to just discharge to a stream, that's fine, but when you want to use this water for irrigation to a golf course, or like a lot of facilities that does that in Kansas, for a golf course, or even irrigation to non-edible crops, then you have to do the chlorination step. So based on your client's requirement, your process may change a lot. But this is the skeleton from where you will start, and as it gets deeper, it gets more complex. Like for each and every equipment, as a process designer, you size it, as well as you take care of the O&M requirements, the cost, and everything. So you add all the details for each unit there as a process engineer. That's what you'll be doing, and then the final process and instrumentation diagram is developed, where the complete details is given. For example, like in pumping station, you have the water operating levels on, off, and then alarms, and your pump itself, there are a lot of specifications you can provide for the pump, like what is the flow rate, it will operate at what head, and so forth. There's so many parameters for each, and that's what a process engineer is concerned about. And even after designing a process, it works fine, and you're taking care of O&M, and it's going to work fine for another 20 years. There's going to be some problem like annual O&M, but after all this, then the optimization enters. Like, okay, then can you reduce the energy requirements, cost for your client? Like, and for example, can you reduce the chlorination dose? Like, you can provide excess chlorination, say, okay, this is a safety factor, and fine, like you use this and you're safe. But what about the cost? Like, then you're just increasing the cost for your client. And similarly for the pump. Like, so there are other factors that you can, and even for screening, like you can have different, like configurations and different kind of process control for screening. So if you have a very fast acting screen, then you're not going to have some flooding, like backflows, but the energy is going to be intensive. So all these parameters, the optimization comes, and based on heuristics or like established optimization methods, you can develop the optimization here. And again, the most important part is the engineering economics, where like for any project, the engineer always considers several alternatives. It's not like a client comes to you with a problem and you just say, okay, this is my solution. You have to provide him like 3 or 4, and that's also the state also recommends that, and there are guidelines for that. And so we develop alternatives, and we also develop cost estimate for each alternative, very detailed cost estimate for each alternative. And it's not sufficient even if you just develop the capital. Sometimes the capital may be very low, but your O&M cost